Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be focusing on acid-base equilibrium. So previously, when we've been looking at acid and bases, what we've been looking at is more or less what happens when I just place an acid or a base by itself into water. However, we're going to slowly be moving away from this. One of the first things we should make sure to consider is that if I've got a strong acid, it really doesn't end up forming any sort of equilibrium. If I put, say, HCl into water, it completely breaks apart into chloride and hydronium. There's really no sort of back reaction. And as a result, the initial concentration of HCl that I put in water is going to be the same as the resulting hydronium or proton concentration. And so generally what we end up finding is that as I end up placing more acid into water, the amount of protons will increase. And as a result, the pH goes down as we become more and more acidic. Now, one of the important things to note about this is there's nothing I can do to drive the reaction backwards. There's nothing I can do to actually make that HCl stick together. No matter what I do, HCl will be a strong electrolyte. So I'm not going to reform this strong acid. And so as a result, if I end up adding a strong acid to solution, this is going to be the same as adding protons or hydronium into solution. And this is going to be a very important way in the future as we go through the rest of this chapter to help modulate the amount of free protons in a solution and figure out how we can affect the reaction. Similarly, we can do the same thing for strong bases. If I take one of my strong bases, so again, all of these are pretty much a alkali or alkali earth metal attached to hydroxide, I put in the water, it completely falls apart. And as a result, the initial concentration of sodium hydroxide that I put into water is going to be the hydroxide concentration. If I make a solution that should be 1 molar sodium hydroxide, this is just a fancy way of saying it's 1 molar hydroxide. And so if I go ahead and try and put in more sodium, this won't do anything to the reaction. Le Chatelier's really won't hold here. And if I add more sodium hydroxide, I'll increase the amount of hydroxide. However, one of the big things that's going to be important as we progress through this chapter is to make note that if I end up adding hydroxide into a solution that has hydronium, it's going to react with any sort of free protons, and they'll essentially annihilate and just end up making water. Now, this is actually going to be a very useful way to help control the pH of a solution. Because if I add a strong base into solution, this is going to be synonymous with removing the amount of protons. So if I add a strong base, the pH should go up. Conversely, I can add a strong acid to remove any hydroxide from solution, again, driving the reaction. So if I want to make the system more acidic, I add hydronium, reduce the amount of hydroxide present. And this is going to be a very important way to modulate the behavior of a weak acid or weak base system. So let's go ahead and see how all of this equilibrium varies as I go to a weak acid. Now, the most notable thing is that strong acids and bases, they don't have an equilibrium constant. They always go to completion. Now, if I've got a weak acid, it's going to have an equilibrium constant, and generally an equilibrium constant less than 1. And as a result, I'm only going to slightly break apart and make a little bit of conjugate base and a little bit of free protons. And so originally when we were looking at the system, if I wanted to modulate the amount of protons present, I would do it by one of two methods. Either I'd choose an acid that was more acidic, so had a larger Ka, or I'd increase the amount of acid I had, which drives the reaction to the right. However, we can also use Le Chatelier's to help really kind of shift our equilibrium. So the easiest way is the one we've seen before. I can add my more weak acid. This drives the reaction to the right, and I'll produce more conjugate base or more protons. However, if I want to break apart my weak acid, one of the other things I can do is add hydroxide. By adding hydroxide, I consume up, nom nom nom, and chew up those protons. With fewer protons present, this means that the reaction will move to the right. And so this is that important idea of one of the ways to drive a reaction forward is to remove products. Conversely, if I want to reduce the amount that acetic acid breaks apart, I can add conjugate base, and this will reduce how many free protons are released. Or conversely, I can add more strong acid, again, read free protons or my hydronium, and this will reduce the amount of conjugate base that is formed. So again, really what we're doing here is making use of Le Chatelier's to control the equilibrium dynamics of an acid-base reaction. Now we can apply these same principles to a weak base, one of the iconic versions here being ammonia. So ammonia naturally breaks apart and forms a certain amount of ammonium and hydroxide in solution. Now it turns out that normally when we're looking at the pH for this system, it's going to depend on, again, the basicity, so how much our given weak base wants to break apart, and the amount of base I add. So we can again shift the system using Le Chatelier's. So again, I can favor the products by either adding a weak acid that will, again, drive the reaction forward, or I can remove hydroxide present in solution by adding a strong acid, which chews up, nom nom, all the free hydroxide, again, removing hydroxide from solution, shifting the reaction towards products, which will encourage the formation of more conjugate acid. Similarly, if I want to reduce the amount of hydroxide released, I could add conjugate acid, which will drive the reaction to the left. Or if I want to reduce the amount of ammonium produced, I can add more hydroxide and again, drive the reaction to the left. So really what we're seeing here is ways we can apply what we know about Le Chatelier to help balance acid-base reactions. And again, making use of the fact that adding strong acid is the same as removing hydroxide, and adding hydroxide is the same as removing free protons. So when we go on the next lecture, we're going to go ahead and look a lot more at this dynamics of balancing a conjugate acid-base pair to help control the pH of the system. Until then, take care.